one more limit here. So here it is. We're going to find this limit now. Now this limit says, as a limit of sine of square root of x squared plus y squared over square root of x squared plus y squared of xy as it approaches 0, 0, what is it? So now when I look at this and I plug everything in, I'm going to end up with the sine of 0 over the square root of 0, which is 0. So I'm going to get 0 over 0 again. So again, I can't just plug it in. Sometimes I can, but I always try that first. Now again, I don't always write it out, but I wanted you guys to see what that looks like. So that's not going to work here. So my other approaches that we've taken in the past, if I look back at this, is I did some sort of factoring. That was one thing I did. I factored up here. And then for this down below here, I found different paths so I could find out that it doesn't exist. And this is some other stuff I did. I split it across multiplication, and that worked. And then another thing I did was I had a square root down there, so I thought about the conjugate, and that's what I multiplied it by. That's what it's called, that idea. The difference of squares idea, and that's what I used there. And then that simplified and worked. So those are the different ideas that I used so far. Now, if I try a square root thing here, that's not going to simplify anything, believe it or not. This is going to be a little bit special here. And the indicator is this x squared plus y squared. What I mean by that is I know x squared plus y squared equals r squared. I'm going to go polar. That's what that means. And that's what's going to help us here with this problem here. Because think about this. If I think about this in terms of polar, then I will be able to just let r go to 0. And then I don't have to worry about paths because I'm taking a radius. And that radius, as it gets smaller and goes towards 0, is going to consider every path. And that's kind of the beauty of this. So that's going to be what we're going to do for this problem. All right, let's get started then. So we're going to turn this thing into polar. So I'm going to take the limit, and let's do the conversions below here. Because I know x squared plus y squared equals r squared, I'm going to take the r goes to 0 here. And this is going to be the sine of square root of r squared. And then on the bottom, I'm going to have the square root of r squared. And then I'm going to simplify that. Now remember, r going to 0 isn't closing around the point 0, 0. So make sure you're comfortable with that idea. So this is really the limit as r goes to 0 of the sine of r over r. Now we've seen this limit already before, because when I plug in my 0 here, I'm going to get 0 over 0. So I write 0 over 0, and that's my justification into using L'Hopital's rule. And I can do this because I only have one variable here. That's what makes it legal. So again, the L'Hopital's rule says if I can use it when I get 0 over 0 or infinity with a limit, then the limit of the original function is equal to the limit of the derivative of the top over the derivative of the bottom. So the sine of r then is going to become cosine of r, and r is going to become 1. So then when I plug in 0 for cosine now, because now I can just plug it in, the cosine of 0 is 1. So I get 1 over 1, which is 1. So there's my answer for this one here. So sometimes polar is handy. That's another technique. So now just kind of doing a recap of everything here. So I can use polar if I see that it works. If I have suspicion that it doesn't work, I can use two different paths, and that's what I did here. I picked x equals 0 and y equals x squared. I can use factoring, and that's what I did for this one here. And this one here, I can use some fancy algebra to multiply times the top and the bottom, multiply it by a fancy 1. And then I could use the idea of multiplication by factoring it in a sense that way. So let me show you something on this one. This one's kind of cool, this number D. I know we worked it out in the last video, and hopefully you watched it. And if not, go back to it. I want to show you something here. But notice here, I ended up with 0 when x equals 0, and a half when x equals a half. This is the actual surface of this one. Now this first one, you can kind of see where I get this parabola shape right here. And you think about the path we used was y equals x squared. That's exactly that parabola. And then when I look at x equals 0, that's going to be this line right here running through there. And that's what we're looking at. Now I want to show you a side view of that. This is kind of cool. So this here is that parabola. And it kind of just goes over the top of that. And we can see why that parabola gave us the number 1/2. And then if I look at the other line, that's my y-axis where x equals 0. And if I take that line, we see why we end up with 0. I thought that was kind of cool. And I wish I would have showed you in the last video when you did this problem, but that's something I just kind of didn't want to let go. And once we started talking about the other problems, that's kind of nice. So you could actually see why you got those two different values. So that's this one here. When I did that limit of that line, you can see why it's 0. And then also why the other one is 1/2. Pretty cool. Anyways, we learned all those different techniques for limits. So now you'll just have to pick and choose, and hopefully you pick the right one. And I think as you do more of these limits, you'll realize what will probably work best for that. That intuition for this is usually pretty good once you do quite a few of these limits. There it is.